Assalamualaikum and greetings everyone. We are still on Stoke's theorem, but today I'm going to show you an example of solving a line integral by using Stoke's theorem, which means that instead of evaluating line integral, we're going to evaluate surface integral. So f dot dr integrate over closed curve C is equal to del cross f dot unit normal vector n integrate over open surface sigma. So how to evaluate this is we project our surface sigma onto region R, and then unit normal vector ds will be replaced by normal vector dA. And the direction of the normal vector to the open surface sigma and the orientation of our closed curve C obeys the right hand rule. So normal vector will be, we're using your thumb to represent the normal vector, to know the direction of the normal vector, and your fingers here would be the orientation of the closed curve. Alright, so as an example, let's look at tutorial 5. Okay, tutorial 5, number 13C. Okay, so for number 13C, let me change the orientation. Okay, so for number 13C, we are asked to evaluate f dot dr by using Stoke's theorem. So it says use Stoke's theorem to evaluate the line integral. So what we're going to do is we're not going to evaluate line integral, but we're going to evaluate surface integral. And here it says that C is a closed boundary of a triangular surface connecting 200 to 210 and 202, oriented counterclockwise when viewed from the positive x-axis. Okay, and then f is given here. Alright, so let's do that. Okay, so this is from tutorial 5, number 13b. Excuse me. So f is given as f is equal to xy, yz, y squared. And here it says that C is a closed boundary of a triangular surface connecting to this 3 points. Okay, let's sketch that. Okay, so here we have the x, y, z space. And we have the 3 points, which are really the vertices of our plane, triangular plane. Okay, we have 3 points. 2, 0, 0. So let's say that's a 2. And we have 2, 1, 0. So let's say that's a 1. So we have, that would be 2, 1, 0. And then another one is 2, 0, 2. So we have 2. Y is 0, and then we have a 2. So let's say that's a 2. So we have 2 here. Yep. Okay, so we have all the 3 points. Now let's connect the 3 points because it says our C is the closed boundary of a triangular surface. Okay, let's see. Let's use blue. So we connect the 3 points. So that would be our closed curve. And it says the orientation of the closed curve is anti-clockwise when viewed from the positive x-axis. Okay. Alright, need more room here. Okay, so it says it is counterclockwise when looking from the positive x-axis. Okay, let's say you are here and then you're looking from the positive x-axis. So let's say that's your eye. Looking from the positive x-axis, and the direction of the closed curve is anti-clockwise. So anti-clockwise would be like that. So that is your orientation of the closed curve. And you can see that the closed curve C is the boundary of an open surface. So here we have the open surface, which is a vertical plane. Okay, so the open surface of the vertical plane here, you can see that it's a plane, vertical plane, which is equal to x equals 2. So that plane, the open surface, is really x equals 2 plane, okay, because it's vertical, only part of the plane. And here you have a triangular shape on x equals 2. Okay, since it says the orientation of the closed curve is anti-clockwise direction, so then you can use the we can use the right hand rule. Okay, where is the right hand rule again? The right hand rule says the normal vector to the open surface and the direction or the orientation of the closed curve obeys the right hand rule. Okay, so from here the direction of the closed curve is given, so using your right hand rule you can see that the normal vector is this way. Okay, so the normal vector that we want is is pointing towards you. Okay, so from there you can see that the plane here is facing the positive x-axis. Okay, and as you can see the direction is towards the positive x-axis, meaning that you want your I, so you have to check for I here, you want your I to be positive. In fact, you want positive I. Okay, you want it positive 1I. Right, you want the normal vector, the x component to the normal vector should be positive 1I. Okay, and in fact you can tell that the normal vector is really 1I, 0j, 0k. Okay, now see here, you can rewrite the equation as v x minus 2 equals 0, and find del phi is equal to 1, 0, 0, and it is the same sign as what we want. We want the x component to be positive 1, so it is already positive 1, so that would be your normal vector. Okay, what we want to evaluate is f dot dr. So f dot dr using Stoke's theorem is equal to del cross f, which is curl of f, dot unit normal vector integrate over surface sigma, open surface sigma. But then how to evaluate this is we project this onto region R, and then unit normal vector nds will be replaced by normal vector dA. Okay, since our surface is given as x as a function of y and z, in this case x is equal to a constant, so when we project this onto, we need to project this onto the yz plane, and you can see that we have a triangle. So this is the projection of your open surface sigma onto the yz plane. So what we're going to do is we're going to project this onto the yz plane. Okay, now we need to get a del cross f because we already have the normal vector. So del cross f is curl of f. Okay, let's evaluate that. So del cross f is a determinant of a 3 times 3 matrix. First row we have the standard unit vector I, j, k. Second row would be the components of del, partial x, partial y, partial z. And in the third row would be the components of f. Components of f are x, y, y, z, and y squared. Okay, now taking the curl of f, cross out first row, first column to get the x component. We have 2y minus y, and then for the y component you cross out first row, second column, you get 0 minus 0, and for the z component you cross out first row, third column, then you end up with 0 minus x. Okay, so simplify this. This is equal to y I 0j negative x k. Okay, now we have del cross f. We also have n. Next is we need to cross the two vectors. Okay, del cross f dot normal vector is equal to, so here we have yi 0j minus xk dot with our normal vector, which is 1i 0j 0k. This is our normal vector. So when you dot two vectors, you get a scalar, so that would be y plus 0, which is a y. Okay, so now we know what to integrate. So del cross f dot normal vector n is equal to y. Okay, and we're going to integrate this over region R, which is on the YZ plane, and our region is a triangular region. Okay, so here we have y. Okay, now your dA is either dz dy or dy dz. Okay, I'm going to pick dz dy. You can do it either way. Alright, so y is the one we integrated last, so now we just concentrate, refer your region R, which is the red triangle there. So y is going to be from a constant to a constant. So y is going to be from 0 to 1. And then to get the limits for z, you just draw straight line parallel to the z-axis across your region. Okay, so the upper limit for z would be the diagonal red line there. And the lower limit for z would be the y-axis. So the lower limit for z is 0. Now you have to come up with the equation of the straight line. This is your straight line. So it's going to be z equals my plus c. So the slope is negative, so we have negative 2y plus 2. So z is 2 minus 2y. Okay, let's check. When y is 0, z is 2. Yep. When y is 1, you get 2 minus 2, so z is 0. So the upper limit for z is 2 minus 2y. Okay, so that's is quite easy to evaluate. So we just back to double integral. Okay, so integrate y with respect to z, we get yz. Now replace y with upper and lower limits, which are 2 minus 2y. Okay, upper limit minus the lower limit, so we get y times 2 minus 2y minus 0. So now we're going to integrate with respect to y. So the first term we have 2y. So integrate with respect to y, we get y squared. And here we have 2y squared. Integrate with respect to y, we get 2y cubed over 3. And then replace y with upper and lower limit. So you have 1 minus 2/3, which is equal to 1/3. Okay, so that's how you use Stoke's theorem to evaluate line integral. So instead of evaluating line integral, you evaluate surface integral, and the direction of your normal vector to the surface sigma, open surface sigma, obeys the right hand rule. So here the orientation of the closed curve is given, so you can determine which direction is your n by using the right hand rule. Thank you.